This video presents the paper entitled A Multitask Vision Model for Multi-Gripper Robotic Grasping. Motivation. Our goal is to allow one single robotic arm to handle multiple grippers to grasp a wider variety of objects. Our contributions are as follows. A multitask deep learning pipeline capable of generating grasping poses for two different grippers simultaneously. A learning-based switching strategy that selects the most suitable gripper for each object. An extensive evaluation, including real-world experiments in industrial scenarios. Method. Given a point cloud of the scene, our method uses a backbone to extract a per-point feature information. Then, the multitask network uses these features to predict graspness score maps for parallel, vacuum, and binary object masks. Afterwards, the graspness scores are transformed into a binary graspability mask and sampled. Then, these sampled points are passed through specific grasping pose refinements. The parallel pose refiner predicts grasp configurations including scores, widths, rotations, and depths. In contrast, the vacuum pose refiner adopts a geometry-driven approach, where sampled points directly generate vacuum poses via normal estimation. After obtaining the grasping poses for both grippers, the mask predicted by our switching strategy module is used to select the best gripper for each object in the scene. Real setup. Real experiments were carried out using an industrial robotic arm, equipped with a real sense, a parallel gripper, and a vacuum gripper. The end effectors used a tool changer mechanism to allow efficient gripper switching on the fly. As baselines, we compared against single gripper methods, SuctionNet 1 billion for vacuum grasping and EFG for parallel grasping. First, for the single gripper experiments, these baselines were run separately over the same set of scenes. Even if our model was capable of generating feasible grasping poses for both kinds of grippers simultaneously, we only selected the vacuum or the parallel candidates to ensure a fair comparison against each of these baselines. In this particular example, for each trial, our MultiGraspNet processed the input point cloud and predicted grasp candidates. The pose with the highest score selected and executed. After each attempt, the system re-evaluated the remaining objects in the scene and repeated the process. The model outperformed the single gripper baseline in both tasks, with particular gains in the vacuum one and competitive performance for the parallel task, demonstrating being a more reliable and efficient option than S1B for vacuum grasping and preserving strong capabilities for the parallel task. To further investigate architectures capable of managing multiple end effectors, we compare our model using the switching strategy module against a baseline combining SuctionNet 1 billion plus EFG. The models of these combined baseline were executed sequentially on the same input, while our MultiGraspNet model is capable of generating multi-gripper poses simultaneously. In this particular example, our MultiGraspNet model, including our switching strategy, is solving the scene. In general, by using both grippers, our model can be exploited to its full potential, preserving perception quality and maintaining a low number of failure attempts. Conclusions. We propose a multitask 3D deep learning model capable of predicting grasp poses for parallel and vacuum gripper in a unified framework. We achieve competitive performance with single gripper models by leveraging complementary information between grasping modalities. We performed experiments with online switching that highlight the advantages of our unified architecture, significantly outperforming traditional normalization approaches.